All right, everyone, we're going to continue here with video 3 of our AP Calculus B final review. And here we get a question about RRAM and LRAM. Question 9 says, Part A, use RRAM with 4 rectangles of equal width to estimate the area of the region enclosed by the graph f of x equals x squared and the x-axis for x between 2 and 6. Now, naturally, you probably should have some idea about how this graph looks, but being that this is a polynomial graph, we can pretty much say that there's not going to be any points of discontinuity in between 2 and 6. Now, if there was a point of discontinuity, we would have to make sure that we do not include that in any of our intervals, especially if it's a break but if it's a infinite discontinuity, then I think we would be completely asked out on this problem. But that's not here or there because x squared is a very regular graph, which you should be very familiar with from, Algebra 1, really. I like to do these problems using a table. So let me get my table set up. Unlike what I see in a lot of textbooks, I really do think that it's important to look at the intervals rather than looking at any individual value of x. So here we have set up in our first row intervals of x. Since we need 4 of them, it doesn't take much mathematics to know we're going to go from 2 to 3 in the first interval, 3 to 4 in the second interval, 4 to 5 in the third interval, and then 5 to 6 in that fourth and last interval. Part A says to do a right rectangular approximation method, so we need to figure out the value of f of x on the right side of each of these intervals. So for example, this first interval is going to be 3 squared, and 3 squared equals 9. This second interval is going to be 4 squared, because 4 is on the right side of the interval. So 4 to the second power, well, that's equal to 36. The next interval is from 4 to 5. On the right side of that interval is 5. So f of x is going to be 5 to the second power, which is 25. And the last one we have from 5 to 6, the right side of that interval is 6. And 6 to the second power is 36. So area is going to be equal to the integral of f of x from 2 to 6. And this could be approximated by the sum of f of x's multiplied by delta x's, which is dangerously close to looking like the integral formula. We're just going to take each f of x, multiply by delta x, and then add all of these together. So we get area can be approximated by 1, which is the delta x between 2 and 3, noting that 2 minus 3 is in fact equal to 1, multiplied by 9, plus the delta x for the second interval is 4 minus 3, or 1, multiplied by 36, plus this delta x, which is 5 minus 4, or 1, multiplied by 25, plus this last delta x, which is 6 minus 5, multiplied by 36. And then hopefully you got that typo. 4 times 4 is actually 16. So when we add all of these together, we get 9 plus 16 is 25. Add another 25 is 50. Add a 30, and that's 80, and 6 more is 86. So we get the area is about equal to 86. Now for part B, we're going to do basically the exact same thing, except for we're going to figure out our f of x is on the left side of the interval. So we have 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. Again, the area is the same thing as the definite integral between 2 and 6. And I'm just remembering that we had to make sure that f of x was either all above the x-axis or all below the x-axis. Since x squared is all above the x-axis, we don't have to worry about positive and negative area, if you will. So we're just going to add together all of the f of x multiplied by delta x's. So we have 1 times 4 plus 1 times 9 plus 1 times 16 plus 1 times 25. And let's see, 4 plus 9 is 13, 13 and 16 is 29, 29 and 20 is 49, 5 more makes 54. So we have our LRAM approximation at 54 units. Which brings on our next question. So we're going to use areas in question 10 to evaluate this integral from -4 to 1 of the absolute value of x dx. Now, I know this question kind of strikes fear into a lot of people's hearts because there is no formula explicitly for integrating an absolute value, and some of you probably would try to find that formula. It doesn't really exist. You do have to approach this as a piecewise function. Now, I hope most of us out there are pretty able to recall the graph of the absolute value of x, and if you are, that would make this process a lot easier. So let's take a look at our two areas here that we need to compute. The first one is going to be from -4 to 0. So in essence, we're going to be integrating from -4 to 0 of the absolute value of x, which we'll do that with yellow. That's going to be this area right here on the left. So here we have a triangle from -4, x equals -4 to x equals 0. This has a height of 4 and a base of 4. So literally using the geometric formula for area, we're going to have 1/2 multiplied by 4 times 4. And then for this last little bit of area, we're going to get the area of this blue triangle down over here. And this triangle has a base of 1 and 1. So taken all together, we have this. The integral is going to be equal to 1/2 of 4 times 4 plus 1/2 of 1 times 1. And that gives us a total of 8.5, or 17 over 2. And ultimately, that means that the integral of absolute value of x from -4 to 1 is 17/2, or 8.5. Moving right along, we have the find the points of discontinuity of this integral, and then use areas to evaluate that integral. So we have on our denominator an x equals, well, x plus 2, and as we know, our denominator cannot be equal to 0. So if we say x plus 2 cannot be equal to 0, then we're also saying that x cannot be equal to -2. Which is right in our interval because the -2 is between -3 and 5. So we know we're going to need two integrals, one integral that goes from -3 to -2, and the other integral that goes from -2 to +5, since there are no other points of discontinuity. So we're saying we can break up our integral to be from -3 to -2 of x squared minus 4 over x plus 2, and from -2 to +5 of x squared minus 4 over x plus 2. All right, let's take this again and take a look at our integrand. We've got x squared minus 4, which of course we can factor into x plus 2 multiplied by x minus 2. Which of course we can do to both of our integrands. And now that we've done that, we can cancel out that x plus 2 because this will make give us a function which no longer has a discontinuity. But remember, that's not exactly the same function that we started out with, because we do have that whole discontinuity, HOLE, whole discontinuity, at x equals -2. Now that we have our integrand simplified into something which is integratable and that we can actually graph, actually what I'm going to do is respect what it says here. It says to use area to evaluate the integral. So let's use area to evaluate this. We know x minus 2 is a very simple function. X minus 2 is a linear function. Looks like it has a y-intercept at -2 and a slope of 1. So we'll draw one of those. This time, when I look at the integral and I evaluate this using area, I gotta actually take a look at a couple of different things here. And the first thing is, of course, from -3 to -2 is this green area right here. And I'm separating that out because that is to the left of the discontinuity. To the right of the discontinuity, I have this area in blue, and that's going to go from x equals -2 to x equals +2, which means we're going to break up this integral over here as well. And then this last area in red is going to be from -2 to 5. These first two integrals from -3 to 2 and -2 to 2, the green and the blue area, those are going to evaluate to be negative because the area is below the x-axis. Now, you could probably save yourself a little bit of trouble just by knowing that regardless of this break here between the green area and the blue area, you're just going to get one solid triangle here with looks like the base of the triangle is going to be, 4, 5 from left to right, and to up and down is going to be also 5. This whole thing should add up to 25 halves. Negative, of course. And then this red area here, just by counting, it looks like it has a base of 3 and a height of 3, so that is 9 halves. 1/2, 3 times 3, of course. And then when you put all of that together, it should be 16/2 or just 8, which is a nice little bit of work for us. So that's our number 11. Let's move on to our number 12 here. We've got, supposing that f is continuous and that the integral from -4 to 4 of f is 3, and the integral from +4 to 6 of f is going to be -8. So the first thing to do is to find the integral from -4 to 6 of f, and then also find the integral from 6 to 4 of f. This question is just playing with the order of integration, where the upper and lower limits can be interchanged at the price of a negative. And it's also kind of playing with our addition of area. So to be sure, we can separate this integral from -4 to 6. We can separate this integral at x equals 4, noticing that the function here, these upper integral, or the upper limit of this first integral, which is 4, that matches the lower limit of this second integral. Again, that's equal to 4. So if they match, these two integrals should be exactly the same. Now we're given the values of these two integrals. It's 3 and -8, so this should just be equal to 3 plus -8, which, well, that's -5. So that's the first one. The integral from -4 to 6 is the same thing as the integral from -4 to 4, plus the integral from 4 to 6, which is negative 5. Now for the second part of this problem, we're starting off with the integral from 6 to 4, which is actually in the reverse order, since if we're going to think about area and integrals, the lower limit should be smaller than the upper limit, which isn't that much of a bother. We can just rearrange those limits, interchange the upper and lower limit at the price of that negative sign in the front here. And since we know the integral from 4 to 6 is negative 8, that tells us that the integral from 6 to 4 in the reverse order is just going to be the opposite of negative 8, or just 8. And then rolling right along to the very last problem of this video, we've got the integral, or no, I'm sorry, getting ahead of myself. We need to find the average value of x squared minus 4x plus 6 over the interval from 0 to 2. Now, I really do try to make a point that everyone in AP Calculus has this formula memorized for the average of anything. The average of any function is 1 over b minus a multiplied by the integral from a to b. And this applies regardless of what that function is. And I find very few places, if any, I can't think of any place in AP Calculus where this method goes wrong. So it is really important, and I also like to say that this is one of the most heavily tested portions of AP Calculus for whatever reason. We're going to just substitute the things we know. We know our x's are going from 0 to 2, so we can change a and b to 0 and 2. And then we can change our f of x to that function, x squared minus 4x plus 6. And so now the only thing left to do is to integrate this and substitute. Of course, we've got 2 minus 0 is just 2. And then we're going to do an integral of x squared and minus 4x plus 6. Take that integral and go from 0 to 2. And then we'll evaluate each piece here. I know the second half here is 0 cubed and 0 squared and 6 times 0. That's all equal to 0, which is nice. 2 cubed, that's 8. 2 squared is 4, and of course 2 is 2. Let's do the multiplication. 2 times 4 is 8. 6 times 2 is 12. And then since everything is going to be, well, it looks as though our first term is multiplied by 1/3. Let's put everything to a common denominator of 3. 8 times 3 is 24. So 24 thirds. 12 times 3 is 36. So 36 thirds. And then we have, what is this? 8 minus 24, which is negative 16, plus 36, 20. And then half of 20 over 3 is 10 over 3. Minus another half is just 10 over 3. So there we have it. Our average is 10 over 3. And that concludes this video. We'll see you in the next one.